In this video, we're going to look at a few simple examples of improper integrals to illustrate the difference between a convergent improper integral and a divergent improper integral. So we're going to start with the integral from 0 to infinity of e to the x dx. This is a type 1 improper integral because one of the limits of integration is infinity. And the way we can deal with this type of integral is basically to replace this infinity by a placeholder variable like b, and then we'll take the limit as b goes to infinity after we evaluate this new definite integral. Evaluating this definite integral is very easy because the integral of e to the x is just e to the x, and then we just use the fundamental theorem of calculus. So after I integrate this, I get e to the b minus 1 because e to the power 0 is 1. However, I still need to evaluate this limit as b goes to infinity. So to do that, I just remind myself what the exponential function looks like. If you graph y equals e to the x, it is exponentially growing. And so as you make the argument of the exponential become more and more positive, that's like moving farther and farther to the right along this graph, and the y values just keep going to infinity. So this limit's going to be infinity because of the first term. And when the limit is infinity in an improper integral, we say the improper integral diverges. So you could try and imagine the area under the curve from x equals 0 to x equals infinity. It's going to be an infinite amount of area, as our improper integral indicates. We're going to look at another problem that's very similar to this one. Instead, it's going to be the integral from negative infinity to 0 of the same function e to the x. The approach is very similar. We're going to replace this negative infinity by a, and then we'll take the limit as a goes to negative infinity. There's no very important reason that we're using the letter a here and b in the other example. It's just common to make the lower limit of integration a and the upper limit of integration b. But you could use anything here like t and t. Anyway, we now need to evaluate the definite integral from a to 0 of e to the x. After I evaluate that, we're going to use the fundamental theorem of calculus again. E to the power 0 is 1 minus e to the power a. We need to take the limit as a goes to negative infinity of this expression. The limit of a constant just equals that constant, so we'll get 1 from that part, from that term. But we also need to think about the limit of e to the power a as a goes to negative infinity. In other words, we need to think about what happens to the exponential function as its argument becomes very, very large and negative. So going back to the graphical perspective, that means you're going very far to the left towards x equals negative infinity. And as I go very far to the left, the y values get closer and closer to 0. So the limit is going to be 0 for the second term, 1 for the first term, and we end up with 1 as the result of this improper integral. When your improper integral just equals a number, then we say that it converges. So you could say that this improper integral converges to the value 1. We'll look at one last example. It's going to be the integral from 0 to infinity of cosine of x, another function that we can integrate very quickly. But as usual, we replace the infinity by b, then we'll take the limit as b goes to infinity We now have the definite integral from 0 to b of cosine of x, which is readily evaluated. The antiderivative of cosine is positive sine, so we get sine evaluated at b minus sine evaluated at 0. Sine evaluated at 0 is just 0, so we can drop that. And now I'll need to take the limit as b goes to infinity of sine of b. However, the sine function is just a function that keeps oscillating forever. If I make the argument of the sine function just keep getting bigger, in other words, if I keep going to the right on this graph, the y values never settle down or approach a particular value. So this limit does not exist, and therefore we're going to say that this improper integral is divergent. The integral from 0 to infinity of cosine of x diverges because it does not equal a number. So in short, if your improper integral equals a number, then we say that the integral converges. Otherwise, we say that it diverges. Often diverging means that the integral is infinity, but then you have these other cases where the limit simply does not exist, and then we still say it diverges.